Oh yeah. Mine.
Wow.
Oh yeah.
I'm gonna have to fix that. Much better. All right. I brought everything except for my iPad where I was going to take notes. So I need to borrow from somebody here 4 pieces of paper and a pen or a pencil. I suppose I could borrow a piece of paper from 4 different people. It doesn't have to all be the same person. Yeah, each group needs to provide their own paper.
Oh man, I wish I had
I wish I had some really cool paper I could use. I did bring the cable so that I could plug my phone into my iPad to keep the phone charged, though. He really gave me 1 piece of paper. That means all the groups got to cough one up.
I have 2. We got another. Do you want 2? You want 2 more?
2 more would be good.
Here you go.
And then the group that didn't contribute paper, do you have a pen or a pencil?
There you go.
Oh, now I have to take extra notes.
Now that's teamwork.
Oh, they labeled their paper.
That's why
It took so long.
All right. Ready? All right. I see how it is.
All right. I don't imagine that any group is going to go over your allotted 20 minutes. And I hope not, because I've eaten up 6 of them already in getting ready. But I had fun with this class. I hope you guys had some fun in the class. I really hope people learned some things in this class. It was the first time we've ever done it this way. I like it. I think there's some things I'll do different next time. But there's a lot of it that I'll keep for next time also. So thanks for helping me explore this. And now tell us what you've learned. Group 2, you're going to go first? Okay.
Oh.
You want to start with this?
Yeah, sure.
You know, a lot of those little injection molded pieces once you get started, huh?
Yeah.
All right, so we're group 2, injection molding. And so for our progress update, obviously our final parts have been made. And our tutorial is complete. So to make our parts, we had to make some minor adjustments to the mold design, including making it fully symmetrical to kind of help streamline the process of making the cam, and also just to reduce the setup time just a little bit. We added these notches, which you can see at the top there, to help break open the mold using like flathead screwdrivers. And we made sure to adjust for shrinkage using the manufacturer provided percentages, just by increasing the dimensions accordingly. So as you can see, we have like a lot of failed parts initially, and we resolve this by increasing the amount of pressure, playing with the temperature a bit, and you can see that there's some discoloration in some of the parts, and that's because of the pretty much the material that was in the mold, the injection molding machine previously. Like the process of getting rid of it is kind of just turning the heat up, putting your actual material in, and just kind of letting the old stuff kind of melt out, try to press it out. So I think Konstantin has a like a kind of a black chunk of like a big pile of the old plastic that was in the machine. So that's kind of funny.
Another thing that I know from previous experience, and this also reinforced it, but the mold itself basically has to warm up before your like shots start to be consistent. and like good. So that's why the first couple, like it didn't go all the way through. And then as it went on, they got more full and the full part we wanted. So if you do try to recreate this, you might have to do a couple shots that are bad first.
As a refresher, the material that we used was Delrin, and that had a shrinkage rate of about 2%, and our starting temperature was about 420 degrees, but we tried to increase this as we went to slightly improve the surface finish. So if you want to talk about that.
So to kind of replicate what we did, it's 2 main steps: making the mold and then using the plastic injector. So you have to design your mold, and you want to do this with the reverse of the piece in your mind. So like we started by modeling the little leg piece and then taking like the inverse of that and carving it out of the stock, like in SolidWorks. And then machine it out, and then once you have your mold, which we use aluminum for, then you just use the plastic injector, which is a pretty simple machine. Plug it in, turn it on, set it to your temperature, put the mold underneath, pull the lever, let it sit, take it out, and you're good to go. And this is our just kind of step through from our tutorial paper that we have.
So just some of the things that we added as well to this, just for suggestions for when you're making your mold. One of the really big things we found was like the orientation within the mold. So, and something we found really helpful was trying to make the mold symmetrical on both sides, because then CAM process is super easy, because you just start doing the exact same thing, and it makes it a lot quicker, because you don't have to upload 2 different programs, and it's just, yeah, it's a little bit easier. And for our orientation, just made it our original part, if you remember, we had some longer pieces going deep into the mold, which would have made it really a pain to pull out our piece. But with this new one, it was all flat in there, so it was really simple to just pop it out.
And it's just steps through how to use the plastic injector. It's very, very simple. And this guy has a good video of it. It's like a minute and a half long. So you just turn it on, set your temperature. We used, this is in Celsius, but we used 430 Fahrenheit for our final piece. Put the beads up in the top of the little dish. There's the mold. Tighten it down. And then you just push down on the lever. Wait a little bit. This is pretty quick. And then you take it out, and you have your part. And yes, Ben.
So, out of curiosity, when you were showing like all of the parts that you made, there was sort of like a gradient. The part that you were passing around, where did about where on the gradient did it fall? It looked like it was sort of middle-ish, but
Actually, it was one of the later ones. I think some of the grayish coloration is from when we were making the vise to cut it with the hacksaw. They just got kind of got dirty.
We were doing a little bit of post-processing. It got dirty in the shop.
Yep. So that thing we were talking about, the color and pushing out the old material and stuff. So I used to work at a plastic injection molding factory, and when they would change colors on the same product or something, you would get about 50 or 60 pieces that were a blend, a swirl of those different colors. And so then they would go sell those like scout store or something like that. So when you're changing the material, it's a problem. So when you've got the brittle material that you use for making whatever, like we made like office trays and stuff for like stacking ladders and stuff. And when you switch from that brittle material to a material that you use to make a bucket, and you forget to switch the material type over, when you drop the box in the warehouse that has buckets in it, you hear them all shatter inside. So that's the thing. So you spent a lot of time figuring out how to do it and to do all the steps.
Yeah.
Now that you know how to do it, if somebody knows how to do the steps from concept to finished part, how many hours of work do you think it takes? Or days?
It depends on the
So
complexity.
if it's something simple like this,
Something like that could take a day.
You can do it.
once you know how to do it,
Yeah.
take 5 weeks to figure out how to do it.
How long was the like machining time once we had it going?
I think it was like 7 minutes and 30 seconds per half of the mold.
So if you know how to set up the mill, you can bust out the mold in under 10 minutes.
Does it press fit into the base part?
Not tried that yet.
So you might have to make another mold.
Maybe.
Any other questions?
If you have any of the parts, just pass them over to me.
All right.
Thank you.
So you want to keep those?
You guys can keep them all together. But I want to see it all work. Maybe we could do final assembly today if everybody brought their parts. Which group wants to go next? Are you guys ready yet? Or
We're guys.
You're still waiting? All right. Let's go to group 3 then. We'll circle back around and get group 1 at the end. Oh, you were the second group, so Rachel, you had to go first anyway.
Yeah.
All right. So we're the 4-axis lathe group again. Our kind of entire objective was to make this little part, was to manufacture a threaded head shaft using EST30 on the 4-axis lathe.
Kind of an overview of 4-axis turning again. So you see there's the first x-axis is the depth of cut. It moves in and out of a tool, or tool moves in and out. The y-axis is perpendicular and it moves in this direction. You see on the diagram. Material usually spins around the z-axis unless you're using a very heavy wide piece that's vertically in vertical z direction, and then the c is the rotation of the z-axis, and it's controlled by servos. Additional part of the 4-axis lathe is the live tooling part, which really allows for a much more complex manufacturing. Again, it is this component where it connects these gears on this side to here and provides a different angle of cut as that can spin and carve onto the surface of material, having to stay along the z-axis.
Sorry. Although we didn't have this update last time, we have finally created a user manual. We have made significant progress on that guide. We have linked it in the presentation if anybody actually wants to view it while we're presenting.
So kind of the first thing to look at when doing 4-axis, lathe CNC milling at all, is to kind of set up the chuck. And so we learned that it's unlike the ones that you used in ME3820 with the interchangeable collets. This one has an adjustable chuck that can hold plates or very large pieces of stock material. So we learned to put the largest set of jaws in towards the center, so we had the most amount of surface contact between the jaws and the workpiece so that it didn't move. And then we had to torque it down and make sure that they're all in the right place, because if they're not, things fly out and we're not here.
So to set the tool offset, so the tool offset is so that the machine knows how far away from what its like kind of floating zero position should actually end up. So you type in the tool number to switch to that tool. You jog it towards the bottom, adjust the position so that you can fit like a 0.5 inch dowel. That's the one that was available in like the normal room. Rodrigo also has a zero setter that you just put on top of the chuck, and so you can see when the tool just like touches it. So that would work better than having to subtract the 0.5 from your measured Z measurement. And so, regardless of which of those strategies you use the fixed measure so that the machine figures out itself what that number is. And then you either subtract 0.5 if you're using a dowel pin, or you just subtract and then you have your final number if you're using a zero setter.
So then you also need to put in stock pieces. You shouldn't have them extend out too far. Thankfully, we didn't have to. This was a very, very small part. There is a support there for the tailstock in case you do need to do that. But generally, just a couple of inches is just fine.
One of the final steps is setting the work offset and make sure this sets the minimum distance that the tool will travel before its material, whereas the tool offset is the maximum distance it can travel. So kind of any type of cutting is restricted to the work offset, the tool offset, and then kind of the radius of the material and put it in the G code. So this is kind of just the instructions of how to do it, and it's all in the manual, and you can go through it again. It's manually.
As for program importing, that process is also the guide, but it is relatively simple. Once you move it from whatever program you're using, whether that be ESPRIT or Fusion, and then put it onto a floppy disk and insert that into the lathe, then you simply list the number of so you have to insert the device first. Then you list the programs, select the file, then do the current commands to double check everything, and then hit settings graph twice and second start to simulate the cutting paths. And if that all checks out, then you're good to machine.
So these were our two final parts. That's it. Yeah.
They took a while to machine and a lot of trial and error. So I'm very careful with them because we don't have to make it up any others.
Yeah, as we mentioned on one of the slides, huge shout out to Rodrigo for helping us as much as he did. We probably wouldn't have been able to get it done on time without it, to be honest.
Yeah. Any questions?
What was the most challenging part of it?
We said the live tooling section.
Between the live tool and the threads.
Yeah.
Because so on Monday, we were able to cut the threads in the machine with the G code that we kind of made. And then yesterday, when we went to go run the same thing, someone had taken out the thread tool, and we didn't know where it was or how to put it back in. So we had to do the second set of threads by hand. We broke two parts of the process, so we had to do it a few times. So that was a little challenging.
See, this is the one that we had to hand thread. That was the one that was machine threaded and onto machine threaded. It was all cleaner. but they both screw on.
They both work.
What's the cut time on the part once you got everything all set up?
5 minutes.
Now that you know how to, so the first time it took 3 weeks to set up. Now that you know how to do it, right? But that's the learning process, right? Now that you know how to do it, how long do you think it would take to set up if you had to go make another one today? How long would it take you to get ready to press start?
15 minutes.
If we had to go find all the tools, we knew where all the tools were, then yeah, 15 minutes. Because setting the offsets now only takes us 1 or 2 minutes. Because
It depends. If you have to move the chuck jaws, you add a few minutes. If you have to install the tool blocks, you add a few minutes.
that all assumes that everything.
But if everything's in the machine in 15 minutes to set up.
Yeah.
So if the jaws are in the right place, and the tools are all in the machine. Yeah. That sounds about right.
I mean, to be honest, that wasn't even like the biggest thing. I think when we went to screw up parts, it would be something with our program, not necessarily the machine.
Yeah. Well, I'm assuming that the program works at this point, right? That's so that's one of the things too in a production job. This may be a part that somebody orders 100 pieces, and then 6 months from now they're going to order another 100 pieces. And so the first time you do it, you have to figure out how to do it. You have to figure out how we're going to fixture it, what process order are we going to use. But the next time you do it, you've got all that information, and so it's much faster to set up and do the next time. So you make more profit the next time. I guess was my point. Okay. Any other questions, comments, feedback? All right. Who's next? Let's have group 4 go next, and then we'll finish with group 1. Since you guys went first all the other times.
Well,
Yeah, I actually did it myself. I saw it.
So I think I would do the next one. Start.
all right, cool. Yeah, that works. All right, cool. So it's our final presentation. So what is fourth axis milling? Typical mill, we just use XYZ movement, but the fourth axis adds an axis of rotation, known as the A-axis in our case.
So the main benefits of the fourth axis is that it adds rotation into your milling operation. The two main uses for it are staggered or continuous. If you use it staggered, you can do what we used it for, which is essentially face off multiple faces of one part without having to take it in and out of multiple machines or doing multiple setups. And then the continuous allows you to do normal milling operations while the piece is rotating, which allows you to do fun things along like arcs, which would normally be incredibly difficult to code in if you were trying to like have the tool move in an arc like that.
Cool. So for first steps for actually making this setup work, the first thing that needs to be done is the fixture plate needs to be bolted into the machine bed, and the pivot point on one of the 4 bolts attached to the machine bed is chosen as a pivot point, so we can adjust how straight the fixture plate is relative to the table of the machine. And then we tram in the plate using an indicator to check the alignment with machine axes, and we try to get it within, I think, 2 thousandths.
Yeah.
Very small offset.
Yeah, that's very much something that you improve at the more you do it. In terms of preparing the machine, you have to go into the settings and enable the fourth axis. The machine has to be emergency stopped in order to do that, which is an important detail. Then you have to insert the probe in the stock, do your normal process of probing the stock, getting its dimensions, and then inserting and probing the tools. One very important detail that we only learned in our final work session is that in order for the rotation to work properly, you have to set your Z origin not at the top of the part, but at the center of the part. So you have to use the offsetting feature of the machine to get the top and then subtract the radius. Otherwise, the machine essentially treats whatever the Z point is as the center of the rotation. So it'll think that you're rotating about the top of the part and do everything wrong.
Yeah. So this is some of our diagrams from CAM. There really isn't much to this. The part that we have today, which I don't have in my hands currently, is not fully finished, but it is as best as we could get it. So yeah.
So if I may, the two main important things in terms of doing CAM when you're specifically using a fourth axis is you can add a line that goes through the center of the part in a sketch, and you can use that line not only as the center of the stock, but also to make sure, sort of like the machine, you need to make sure that your origin that you're using on any given operation is again on that center rotating line. And so there's a feature whenever you add an operation is you can set the mill to that setup WCS origin option. I'm not entirely sure what it means, but it just makes sure that it stays in the same location. But you can see the orientation of the axis will actually switch when you're switching which face you're operating on.
Yeah.
So that allows it to keep orientated at all times.
A little more details on this as well. In order to get this center line, a plane needs to be made in the middle of the two faces of the part in order to get that center drawing line as our rotational axis.
Yeah. So this is the design for our part. As mentioned, so it's got the main features of, a hole to put the bearing in and the plane for that to sit on, and the holes on the back to put the injection molded feet in.
Yeah.
So cool.
All right, so production plan. The first step would be running the part or the stock, the cylindrical stock in the fourth axis. And do you have the part on you?
Yeah, it's going.
Yeah, so it's going around. The part that you have right now, it has the round end on it. The issue with the fourth axis is we can't actually cut the part off very easily. So the plan would be to use the lathe to finish that operation. So it is a completed part. It is very hard to do that on this machine, but we did it. We did as much as we could, I guess.
Yeah. So, we don't have permission to watch videos, but there are videos in there of the production. I guess they're not that important.
You can request access.
Oh, what's that?
Okay, maybe not.
Yeah, we'll figure that out.
I can send you the videos
Yeah,
later.
so the important parts is we had a video demonstrating the tool coming down and then up and then the piece rotating and the tool coming down again. And then
the other video was the part after being machined just rotating in the fourth axis rather slowly to give a good look of all the
Marketing video.
Yeah, pretty much.
That's actually, you'll see it in the next slide actually because I made it again. But I had something else I was going to say and then I got distracted by this.
Yeah, there we go. So this is actually what the rotational video looks like for the marketing as you said. So, yeah.
So in terms of production, so obviously we got two of the faces and the bearing holes. We weren't able to get the rest of it because we only managed to get this on Monday, and it's very hard to schedule machines out when it's finals week and everyone wants to work on the machines. And so that's about as far as we were able to get with the part, but we managed to make the fourth axis work the way we wanted to. So
you didn't do the holes on the backside?
Yeah, I think it was, we didn't have.
Test their part to see if it fits.
Unfortunately.
So we'll just have to assume it's going to work.
Yeah, unfortunately, we couldn't find a what's it called, a head that was a drill bit that was small enough in a reasonable amount of time. So,
dang.
Yeah.
I mean, yeah, like we've struggled so much with this. We had a lot. If we didn't have to try and design a fixture plate for the first couple of weeks, and we rather just bought a fixture plate from the start, I think we would have made more progress and actually had a more completed part. So, I mean, at the end of the day, this class is all about learning. We learned a lot, so we learned what not to do, which is try and design a fixture plate when there's stuff on the market. And we learned all the headaches of using a fourth axis that is rarely used around the shop. So, yeah.
Any questions?
Since you can't do the batch hole because it comes from the drill bit to do it.
Yeah.
At the moment that they were looking
Why do you
at.
just use a mill and do part of the operations?
Or well, the mill head that we were using was larger than the hole. So
It wouldn't have worked,
yeah.
unfortunately.
and it was one of those things where, again, because we sort of talked about this in previous presentations, but because the fourth axis kind of sticks up, there's always a concern of crashing into the thing, and so it took us a while just to set up one mill that we were using, and so we didn't want to,
You don't have extender for that.
we did not get forgiveness standards. We just kind of had to let it hang out a little. We didn't actually get around to that. We can take a crack at that because the bearings are just kind of sitting out in a box, right? So we can
In the drawer.
in the drawer, yeah. So we can. We never got around to that, but we could test that if we wanted to.
So I have one thought. So your problem is you can only work on 5 of the 6 sides of the part, right?
Yeah.
And so one small change I think you could have made that would have made it so you could break the part off or get the part out easily without having to go to the lathe would be to have the stock material be a little bit longer, so that on the back side you come around closer to finishing the circle part,
Right.
and leave a little tab there, and do that operation last, so that when it's done you just break it off.
That
It's similar to what you do in EDM, right? You leave a little tab and you pull the part out so that it doesn't fall during the operation. So that would be sort of a process improvement, would get you to that point where you could make this in production with this setup. It would leave a mark there, right, from where you broke it off. And so you hit that on a buffing wheel or a sander or something to clean that up. If that was sufficient to the needs of the part, would be one small improvement that would have made that part of it easier for you.
Would that cause issues with how much force is being applied to a longer length of stock?
Absolutely, because the longer it hangs out, the more deflection you're going to see. So you got to worry about cutting forces and things like that. The other thing is they make right angle tool holders, and you can put a slitting saw on a right angle tool holder, and slice it off in here. That's beyond the scope of this project. It's just like solutions to the issue that you came up with. That's what I'm talking about.
That makes sense.
Having a tutorial that gets people so that they can put the fourth axis in the machine and do a quick setup and do that will enable more people to use it more often.
Right.
So I think that part of the project was successful.
Yeah.
Really wanted to test if their injection molded.
We also wanted to test.
Yeah, we also did. And before we wrap this up, once again, like Group 3 mentioned, we just got to give a big shout out to Rodrigo for really helping us out, because without him, we would have been screwed. So, yeah.
All right, thank you.
So your shout out should be bigger than theirs, because I had assigned him the task of helping you at the beginning. He just volunteered to help you guys.
He's like,
Thanks. And Group 1.
No, not really. I never get to see it.
Oh, yeah. We're going to have to swap around.
So we are the electrical discharging machining group, and to just go over what we're going to talk about in our presentation, we're going to start off by sort of recapping some of the information we've talked about in prior presentations, and then we will jump into the actual process and more of our guide for this project.
So just a little recap of what EDM is. It's a form of subtractive manufacturing. It uses electrical discharges or sparks to perform the features, the wire or the sintering machine will touch it, it'll spark, and it'll erode the metal. The parts must be electrically conductive or it won't work, obviously, because you need that spark. And there's two types. There's die sintering and wire cutting. The die sink EDM is like conventional sinker EDM. They remove material from the mold using like a graphite electrode that rides above the material. Then the wire cut obviously has the wire that'll be dragged around in the material, cutting as it's going through, creating that little gap.
All right, so reviewing some of those pros and cons when we first talked about this, these kind of dictated one of the reasons that we're making our gear with wire EDM made these to us, but some of them are also for more industrial applications. So some pros, kind of complex, really small shapes. For us, that's gear teeth. That's a involute profile is a pretty complicated thing with a lot of small individual edges and surfaces, or tinier tapered holes. So making a really, really small hole. The sinker, as we were talking about, you have a little bit more. You're able to cut that, which you might not be able to with a drill bit on conventional machining. Very hard materials. For us, we only were cutting AL661, so pretty ductile, easy to machine if we were doing this in a mill. But if we wanted to make this out of stainless steel, tungsten, anything like that, we also could have done that. And also maintaining very fine tolerances. So we actually just got to try our gear on one of the shafts, the hex fit. At least one of them that I tried was a very, very nice like running fit. So that was, I'd say that both of us maintained our tolerances pretty impressively, and we're pretty confident in ours being like within the range that we set for ourselves. There are a couple of cons though. So a skill set required for machine operation. When we wrote this and talked about this at the beginning of the term, we didn't even have the same sense of scope as we do now, that there really is a skill set involved for machine operation. There's a lot that goes into it. There's a lot that can go wrong, and making sure that you actually are able to do that is pretty important. Material removal is pretty slow, as we mentioned, and we'll talk about again. It is a very time-consuming process for the actual like total cutting time. And also overcut, which is something that we also discussed when we actually formed our gear teeth, but that you do need to account for the fact that there is a cutting diameter, essentially, of the tool you're using. It's not cutting an exact fine point. Yep. And then for gear design, so as you mentioned, we wanted this RC7 running fit, which we believe we achieved. And the actual like mechanics to get there, or really the numbers that we were going off of from our CAD model that we were trying to achieve, are this inside 0.375 plus or minus thou, and then the actual just gear teeth themselves are modeled size-wise, but I'd say that we achieved that pretty effectively. So moving on to just like some of the machines we were using for this operation, the two main ones that would need G-code were the Hosmay mill and the wire EDM itself. Just reiterating that they sort of have similar travel distances. They can hold a pretty decent amount of weight, but as Sam was mentioning, the EDM is a much slower process, and it ends up being a much longer process than what you need to use for the mini mill.
So I can talk about the ESPRIT Setup first. So I assume people here do the ME3820, so they should have somewhat familiarity with ESPRIT at some level. Now that I go to so much detail here, we have a user guide that have a pretty detailed ESPRIT portion for doing at least writing the ESPRIT program for the machine operation. But it is always good just to ask for help if you just don't know what's going on in the software. So there are three general steps that's required to do the ESPRIT program. The first one is draw the center hole, and the second tool is EDM the center height profile and EDM the gear tooth profile. So before you put the entire thing onto the machine, you need to finish with ESPRIT, and you need to prepare your stud. First, you need to cut stud with the bandsaw, and you want to use a sanding wheel to grind out the edges to kind of deburr it, so you don't have very sharp edges that might touch you or it might say noticeable in the vise when put in the machine. Then you should face up one edge with the manual mill, so you have a right angle for both the
water offset in minimal and water offset in the EDM machine. Once you have one straight edge, use the minimal to draw the two hole for the wire to go through when it has a head profile in the middle, because the EDM wire cannot go through a aluminum piece. It's just not gonna happen. So once you're finished, your car should look something like this. Then you can put that into the EDM machine to cut your gear.
So moving on to the EDM, the first thing we start with, or the first thing you would start with before even turning on the machine, is fixturing the workpiece onto the base plate. And the important thing to know about the base plate is it's supposed to be a very flat surface that isn't damaged. And so when you are mounting your workpiece, you want to make sure to have a spacer under the actual stock. And on the back bolt, you want to have a penny in between the bolt and the work plate or the base plate surface, so that you're not damaging it and making it an uneven surface. And when you're tightening down the bolts, you want to make sure to use the Allen key or the Allen wrench in the longer orientation, because that way you don't over torque down on the bolts and damage that base plate surface. And then moving on to the next EDM steps. Once you've turned on the machine, you're gonna basically run into setting up your reference points. And the reference points, and even though you've used the right angle tool to square the workpiece on the base plate, you need to set up the reference points so that it can calculate the slight difference in angle at which the piece is from the base plate. So if it's canted slightly, that even if you can't tell by the human eye, it's going to calculate that and account for that. And after that, you're going to set your origins, which in this case would be in this foreground piece. And your RP2, your reference point 2, should be closer to the origin when you're setting that up. And when you're setting your origin up, you also account for the radius or the diameter of the wire you are using. In this case, we were using 1 thou diameter wire.
So after you set the piece into the machine and you set the origin of the pretty much you did the offset for the workpiece, you want to use the remote to judge the upper top. So that's the upper holder of the wire right above the workpiece. That is how you set your upper Z limit. You do not want this to touch the workpiece, otherwise you're gonna start dragging the workpiece. We're gonna stretch the machine. So just make sure it's hovering above, but you want to be close. You don't want a long wire hanging out on the machine. That just doesn't work well. Then you load the machine, load the program onto the EDM machine with a USB. You select minimal, you simulate on the EDM machine, then you load to online. Then you want to fill the tank with DI water. Then you want to set the spillway to slightly below the water level, so the DI water can somewhat settle through. If you put it too low, it's harder on the pump. So the final few steps is you want to check your iron concentration level. It should be, if I remember correctly, it should be around 0.5 or 0.2. You don't want your iron concentration to be too high. And you want to verify the material parameters, and that will kind of let the EDM machine automatically select the, I think it's a voltage feedback on the wire. And you want to make sure the wire is at the starting point. Then you can just start the machine, let the EDM do its thing. Make sure in your program you have thrust stop selected. So when the EDM wire almost finish it cut off, it kind of stops. So you can fish your cut off piece out before the EDM machine moves to another operation. Otherwise, you might just drag the part, because the piece that fall out of the part will kind of taw down the wire, and the entire thing will just be dragged by the machine. We don't want that to happen, because that will move your part out of the original place, and your entire setup, you have to reduce setup if that happens. And also, you just keep an eye on the wire. I don't know what's wrong with the machine we have. The wire sometimes just doesn't work and start to bundle up. And when that happens, you need to hit it up and you need to reset everything.
So we finished. It gets used often by inexperienced users.
Yeah. So we finished our guide. It covers everything from the ESPRIT to the stock to the wire EDM. you'll see, we'll just do a scroll through. There's all the table of contents. The important stuff is at the bottom.
But
The
yeah,
wire.
so this
There we
gives a
go.
pretty detailed list of steps on what you need to do to basically, from the start in ESPRIT, make the gears with EDM. And while we think that we've done a pretty good job listing out every step that would need to be done, we were not able to have this guide tested. And if it were to be used in the future, we definitely recommend having it reviewed by you, Mr. Bertram, or someone else in the shop to make sure that all the steps are, one, correct, and two, explained properly or easy enough for other students to understand.
So, I mean, we handed them out. We finished our gears. We were going to try maybe some reruns, cut some more, but actually right now the EDM is not working again. The little remote does not work anymore. We don't know why. So we've really just been, we've just been waiting for to integrate tests with the rest of the class.
All right, and then when we had our last presentation 2 weeks ago, we still fielded a couple of questions that we wanted to go over just to quell anyone's fears. So one of them was just, what is the biggest issue you encounter with EDM? And I think we kind of touched upon this just in our presentation, that's reliability. During our own operation, we were very fortunate the day we made those gears that things went like relatively well, I'd say. We didn't have huge problems, but if right now the machine is down, it's been down for other periods of time, or even during operation where it's not fully down, but having to do like kind of intermittent maintenance, like that idea that you need to babysit the machine while you're operating that is kind of our biggest like issue that we've encountered. So if things hadn't gone completely our way, we very well couldn't have our gears if our hand didn't work out that way. So that was probably our biggest issue, especially with like actual operation. With the ESPRIT, there was a little bit more back and forth to like get that to a level that we were happy with and that Joel was content with compared to the other machines, but still that kind of came to fruition pretty early. Someone asked, is it intimidating to use the wire EDM? Should I worry about losing figure? And I think that's like, maybe if we haven't made that point well enough with like what we've shown off is that this is a dangerous machine. Like every single machine in the shop is dangerous. But like, yeah, like I stand a little bit farther back from it while it was running and we were watching it. But I think it's really just, it is one big contained system. So as long as you're being smart and you're willing to ask questions, if you don't know what's going on with something, you know where the e-stop is, all of those things. I'm not personally worried about losing a finger, but I wouldn't like stick my head into the tank. And then is there a concern with sharp edges on the part? So I think we've passed them around. If people want to check it out, they can. There weren't really any burrs, which we were pretty impressed with. If there were, like our solution, that probably would be a very, very gentle filing job or a tumbler or something. But I think we're pretty happy with how those turned out.
So with the question two, I just want to mention, sometimes you need to open the trace for the wire to face the wire, and if you don't stop the wire being energized, the entire wire system will have like 60 volts, so you will not lose a finger, but you will be electrocuted. So that's that. And any questions?
Any questions? Okay. That was it, right? You have 4 groups. Here's your part. So I'd like some feedback about thoughts for doing this next time. One thought I had when we were doing presentations today could be that each group has the same task to make a specific thing. I kind of like the way we broke it up though. Everybody got to experience a different thing and got to share what they're experiencing. But I could see where if 2 or 3 groups all had a task to go learn to set up the 4th axis and build some materials to help with that, the groups could talk to each other and help each other a little bit. I just wonder if you think that would work better or worse.
Might be an issue for people that are like if you like Rodrigo that was helping the other groups, if you know you had someone like him having to help 4 different groups,
Yeah.
it might be a bit of an issue.
I think the original idea of it when we formulated it back, whatever it was, 5 weeks ago, where each group would spend a couple weeks making a guide and then the other groups would test out the guide. So to do something like that, the chunk would have to be smaller, right? So, or even the guide building would have to happen at the moment of learning the steps, right? So if your first step was put the work plate in and tram it so that it's square. If you had written up instructions, I'm not saying you should have then, but like if we had designed it so that you had written up instructions during the first week for the steps of doing that, and then somebody from another group got to go test those instructions as part of their thing for that week, then as we're building the instruction sets, everybody gets a little bit of feedback for how that thing works. Maybe so still break up the part into a bunch of different processes, but have firm deliverables about incremental steps along the way, maybe.
I guess first half of the week is like exploring the instructions. Second half is
Yeah. Yeah. So if the beginning of the week, if the beginning of the week you figure something out, at the end of the week you learn something from some other group, but it doesn't. Each person doesn't have to do each of the steps, but if each person does somebody else's other step, it helps bring the whole thing along.
I think that might work if you do something with like if you do something with like standardized parts, just like part of the thing.
Yeah, part of our problem is we were designing the part and learning how to make the part.
So I think we had parts like ahead of time.
Yeah, so if we pre-design the parts, so we know what the parts are, we know what the processes are, that would make it a lot easier.
I think what you're saying about like having essentially there be more structure and oversight on what the teams are actually doing, I think would definitely be a big benefit.
I think it worked pretty well.
I'd say dedicated lab time, like integrated with the class. So like just already I take 2 sessions a week. So like we have like the lectures, we also have like lab time like blocked out already. So we have like that guaranteed amount of time a week because like some weeks we wouldn't be able to go in.
Yeah.
Times. Yeah.
Yeah, I'm gonna talk to the administration about that because when this class was designed, there was no specific lab time dedicated to it, but it did have full-time TAs, and each group would sign up for like 6 hours of lab with one of the TAs each week. And there was some structured labs that we did, and then there was some freeform labs more similar to this. And when new management came in, people were assigning workflows and things, and they had never been to the class, never taught the class, and didn't ask how the class worked before deciding how to assign resources to it. So we have to fix that. And one way to fix it is just to have assigned lab times. I know the reason they did it the other way was to give people more flexibility about when they would go to lab, because we had 40 hours a week of coverage with TAs, so you could pick any time. And some of the TAs would work in the evenings and stuff, so it was actually pretty nice. That was a good setup. So, branch of congressman, maybe we get that back. Anything else? I think it went pretty well. I don't think I gave you a feedback assignment, assignments for today. I am going to do one more feedback style assignment that I have to post, and it's going to be personal introspection and also talk about the group dynamics and that. And I'll ask a question to rank the group. So each person can rank each of the groups and what they. It's just feedback, right? 80% of the grade is participation. 80% of the grade is having a question showing up. And only 5% of the grade is based on my opinion, how well you did. I think 10% is based on your personal opinion about how well you did. 5% is based on your peers' evaluation. So I don't think it is history on grades. I think we're going to fine on grades. And I liked it. I wish we made more parts faster. And I think we've talked about some ways to get that stuff next time. So thanks a lot. Yeah.
You want these parts?
Do I want these parts? Yeah. All the parts in the bag. All the parts in the bag. I want your mold too. Is it in the drawer? What's your mold too? Oh, you want it? Do I actually want the parts? No. Because I can't assemble it. Because if we don't have it all finished, you know I don't want the parts.
You're the chef and the American.
Yeah, I can assemble parts of it, but I don't fidget with it. So no, I don't want the parts. You guys can distribute the fidget toy parts amongst yourselves to fidget with.
Guys, we'll all get together over these.
Yeah. Hey, you know, you could also finish that in EDM. They could cut that out for you. All right. Hey, thanks a lot.
Hey, we have all that stock we didn't get to use.
No, I have all that stuff. And this is why I said don't cut it all up at once.
This is why I should have kept it instead of putting it in the bin.
So that when there's leftover stock,
So you just said it was in there. It's still there.
hey, Pen. Thank you. Thanks.
Sure you don't want these beautiful parts?
No, I don't want them.